Greetings, math people. Today we're going to look at some physics formulas for motion. And what we're going to do, we're going to derive these formulas using calculus. Or for some of you, we're going to verify or confirm these formulas using calculus. The first physics formula we're going to look at is the formula for displacement with constant acceleration. In fact, all of these formulas we're going to look at are formulas for motion in physics, and they all deal with a constant acceleration. So on the board I have the formula for displacement with a constant acceleration, where it says the displacement delta x is 1/2 the initial velocity plus the final velocity times delta t, which is the time interval. So again, delta x, this is the displacement, is 1/2 v sub I, that's the initial velocity, plus v sub f, that's the final velocity, times delta t, which is the time interval. So I'm going to give you the equivalency of these variables in calculus and then go ahead and figure out the formula utilizing calculus. So first I'll look at delta t. So delta t is the time interval. So when we do these type of problems in calculus, we do it from a time where t equals a to a time t equals b. So the time interval for us is between a and b. So therefore, delta t would simply be b minus a. Again, b signifies the ending time and a signifies the starting time. Now, again, this particular scenario is dealing with a constant acceleration. So we can say that the acceleration function is a constant. So that's how we say it in calculus. A of t equals some constant k. And therefore the velocity function is the integral of this acceleration function. So the velocity function, which I'll call v of t, that's the integral of the acceleration function with respect to time. So the integral of a of t dt, which of course is the integral of k dt, which of course is kt plus c. So again, in this model, our acceleration is some constant k. So therefore, the velocity is k times t plus a constant c. Now, c is actually the velocity at time t equals 0, but don't confuse that with the initial velocity, because the initial velocity as given in the situation doesn't necessarily have to be when t is 0. It could be when t is any particular number. So this is my velocity function. This is my acceleration functions. So from this velocity function, I would like to calculate the initial velocity and the final velocity in terms of this calculus notation. So again, the ending time is b and the starting time is a. So my initial velocity would simply be v of a. So this function in terms of a, so v of a would simply be k times a plus c. Ka plus c. Now again, this is equivalent to the initial velocity, so this is the same thing as v sub I in the physics formula. And again, my final velocity would be plugging in b for t, so in the velocity function, so v of b, which would be kb plus c, which is equivalent to the v sub f, or final velocity in the physics formula. So these are the equivalencies. So remember that delta t is the same as b minus a, v sub I is the same, or the initial velocity is the same as ka plus c, and v sub s, or the final velocity, is the same as kb plus c. So we'll work out the calculus and then we'll transform the terms in terms of this after doing a little bit of algebra. So let's go ahead and calculate the displacement. So for us in calculus, displacement, and I'll call it delta x, And displacement goes over a time interval, so it's not something that happens instantaneously. It's not at an instant, it's at an interval. So I'm trying to find the displacement over the interval from time A to time B. So we take the integral from A to B of the velocity function. Now again, the velocity function is kt plus c. And we integrate with respect to time. So the solution of this is going to represent the displacement. Okay, so if we integrate kt, we're going to get 1/2 t squared. 1/2 kt squared plus ct to be evaluated between A and B. So the integral of kt is 1/2 kt squared. The integral of c is ct with respect to t, of course, and we're going to evaluate this between A and B. So the evaluation here comes from the first fundamental theorem of calculus, and what we do is we plug in B for t and then minus plugging in A for t. So let's go ahead and plug those values in and see what happens. So if I plug in B for t, it'll be 1/2 kb squared plus c times b, and then minus, so this is the result of plugging in B for t, so now I'll plug in A for t, so minus 1/2 ka squared plus ca. So there it is there. So let's say we do the subtraction. So I'm going to distribute this negative sign. So 1/2 kb squared plus cb minus 1/2 ka squared minus ca. Now I'm going to do some grouping and then factor out common factors. So I would like to group these two guys together. And I'm going to factor out the common factor that you see in both of them, and that would be 1/2 k. So if I take these two and factor out 1/2 k, so I'm taking out 1/2 k, I'll be left with b squared minus a squared. So 1/2 k times b squared minus a squared. And if I look at these two terms I haven't touched yet, and factor out what they have in common, and that would be c. So I would factor out a c, so plus c, and what would be left would be b minus a. And so that's what we have thus far. Now, b squared minus a squared is b minus a times b plus a. So this guy is b minus a times b plus a. So 1/2 k b minus a times b plus a. So all we did is factor this and still plus c times b minus a. Now you have two guys here. You have this product and you have this product, and both of these have a common factor of b minus a. So I'm going to factor a b minus a out of both these. And so that will be b minus a. And then what's left would be 1/2 k times b plus a. 1/2 k times b plus a. And then also what will be left would be a c plus c. Okay. So now what I would like to do is distribute this 1/2 k times the b plus a. So we have b minus a, and then we do the distribution. So that'll be 1/2 KB plus 1/2 KA, and then of course plus C. Now the next thing I'm going to do, it may not be that obvious, but you see this C right here? I'm going to cut this C in half and turn it to 1/2 C and 1/2 C. Because I want to put 1/2 C with this term and another 1/2 C with that term. So I'm not changing the value of the expression because 1/2 C plus 1/2 C is C. So I'm just going to split the C you see here up into two 1/2 C's. And it's going to look like this. So I still have the B minus A times 1/2 KB plus 1/2 C. And again, that comes from that, plus 1/2 KA plus 1/2 C. And so that's the reason I broke this C up into two 1/2 C's to combine them like so. Because if you notice, everything in here has the factor of 1/2. So I'm going to factor the 1/2 out. So I'm factoring the 1/2 out. I'll put it in front of the B minus A. So this is 1/2 B minus A. And so when I factor the 1/2 out of these, I have a KB plus C plus KA plus C. And now we'll substitute what things were with respect to the physics formula. So if you recall, B minus A was delta T, 1/2 delta T. And KB plus C was the V sub F, the final velocity. And KA plus C was V sub I, the initial velocity. And so what you should see here in a different order, but obviously the same thing, is the displacement formula as given in the physics formula up here. So that's how we can derive this displacement formula utilizing calculus. Okay, the next physics formula we're going to look at is velocity with constant acceleration. So this is the physics formula where it says the final velocity is the initial velocity plus the acceleration times delta t. So just want to remind you of our calculus equivalencies, and that is that delta t is b minus a, and that v sub I is k times a plus c, and v sub f is k times b plus c. And also, of course, the acceleration is just some constant k. Now this one is pretty simple to do. To justify this or derive this particular formula, what I'm going to do is I'm going to integrate the acceleration function from a to b. So I'm going to take the integral from a to b of a of t, which is k, with respect to time. So the integral from a to b of k dt. The integral of k, of course, is kt. So this is kt to be evaluated between a and b. So we plug in b, we plug in a, we take the difference. So that is simply kb minus ka. Now, kb minus ka is v sub f minus v sub I. Again, here's v sub f, here's v sub I. If I subtract these, the c's would cancel, and I would be left with kb minus ka. So this is the same thing as v sub f minus v sub I. So I have two deals here. Now, here there's a common factor of k to both terms that I'll factor out. And so this would be k times b minus a equals v sub f minus v sub I. Okay, so what's k? Well, k is the acceleration function. So that's acceleration in the physics formula. What's b minus a? B minus a is delta t. That's the delta t in the physics formula. And of course, v sub f minus v sub I are already in the formula, the physics formula. So to solve this for v sub f, we'll simply add a v sub I to both sides, and we'll get v sub f is v sub I plus a times delta t. That one was fairly straightforward. So again, that's the calculus. It's a calculus way of deriving the velocity function with constant acceleration. Okay, so now to our third physics formula. So this is another displacement formula, a little more intricate than the first one we did. So this one is stating the displacement is the initial velocity times delta t plus 1/2 the acceleration times delta t squared. So we're still going to get the displacement via calculus by integrating the velocity function from a to b. So therefore our displacement will be the integral from a to b of the velocity function. The velocity function, if you recall, is k times t plus c. So we're integrating that with respect to time. That particular integral would be 1/2 k t squared plus c t to be evaluated from a to b. And then when you plug in b and a and do the subtraction, you get 1/2 k b squared plus cb minus 1/2 k a squared minus c a. Okay, I mean we've seen this guy previously, so what we're trying to do now is simply to make this expression look like this particular expression. So one thing we can do is, again, we can isolate these two together, and we can isolate those two together, take out the common factors, and do some manipulation. So here, again, the common factors are 1/2 k. So I'm factoring out a 1/2 k from both of these. And so I have 1/2 k. And again, what I'm left with will be b squared minus a squared. Now I'm going to stop there because I'm going to add some stuff to this. Now here's the deal. I want this expression to look like this expression. And right here, I have 1/2 k. Remember, k is the acceleration. So I have it's looking like this 1/2 a here. The only deal is this 1/2 a is being multiplied by delta t squared. So I would like the expression inside here to look like delta t squared. Now remember, delta t is b minus a. So if you recall, delta t is b minus a. So delta t squared is b minus a squared, which is b squared minus 2ab plus a squared. So I would like this guy to look like this guy. So I'm simply going to make it look like this guy. So I need a b squared. I have it. I need a positive a squared. I have a minus a squared. So I'll add 2a squared to this. So I'm going to add plus 2a squared. So negative a squared plus 2a squared is a squared. I have it. I need a minus 2ab. So I'm going to put minus 2ab. So if you add all these guys together, they represent this. They represent b squared minus 2ab plus a squared, which is b minus a squared. The only issue is that I added these two guys out of the blue. So 2a squared I just added, minus 2ab I just added out of the blue. So I'm simply going to add their opposites to balance it out. So I'm also going to do minus 2a squared and plus 2ab. So I haven't really added anything. So I've added 0. So these balance out. Now, so that takes care of these two. Now here, still left, I have CB minus CA. If you factor out a C, that'll be plus C times B minus A. Now, of course, the reason for me adding these two guys is so that I can add this up into terms into delta t squared. So these four terms here represent b minus a squared, or delta t squared. So all of this is going to turn into delta t squared. This part is going to be left over. So let me write that. So I have 1/2 k, and again, I just write this how it's written in physics. I'll write this as delta t squared. So 1/2 k times delta t squared. But I also have 1/2 k times these two guys. So I'm going to go ahead and multiply the 1/2 k times these two. So 1/2 k times negative 2a squared, that'll be minus k a squared, and 1/2 k times 2ab, that would be plus k a b. Again, you still have this c times b minus a. Okay, so again, we have the 1/2 a times delta t squared covered. So now the next thing is to make all of this look like the initial velocity times delta t. So let's see what we can do. So we'll factor out what is common to both these terms, and that would be a Ka. There's a Ka common to both these terms. So 1/2 k times delta t squared. And I'm going to factor out a positive Ka. So plus Ka. So you see, when I factor out positive Ka, I'm going to be left with minus A and positive B. So I'm going to write that as B minus A times B minus A plus C times B minus A. So if you look at these final two terms, they both have a factor of b minus a common to both of them. So I'm going to factor that out. So again, I have 1/2 k times delta t squared, and I write k as a. I'm going to start writing it in the physics form. So that's 1/2 a times delta t squared. Now again, these two guys, I'm going to factor out b minus a plus b minus a. And when I factor out b minus a, what's left is Ka plus C. Ka plus C. And, okay, what is b minus a? B minus a is delta t. So 1/2 a times delta t squared plus delta t. And what's Ka plus C? Ka plus C is v sub I times v sub I. So again, not in a perfect order, but you can clearly see the expression came to this guy, which is the same as this guy.